Learning objective for this lesson is to outline and use Newton's second law, a very simple relationship which we established in previous lessons. Before we look at that, we want to just quickly jump back and have a little look at another concept we previously looked at, which was equilibrium. So we say that when all forces acting on an object balance each other out, we say that the forces and the body are in equilibrium. So the net force equals zero, well then it must be in equilibrium. And we do have two types of equilibrium. First is static equilibrium. In static equilibrium, the net force on the body is equal to zero and the body is at rest. This is in contrast to dynamic equilibrium, in which we have a net force on the body equaling zero and the body is in motion. Now, this might remind you of Newton's first law, this previous slide we saw, and it's no coincidence. This third component of the law, which says unless acted upon by a force, well, guess what? That's our net force. When we have a net force, when objects remain stationary, they are in static equilibrium. All the forces balance each other out, or there are no forces acting on it. When the object's in motion and it remains in motion, it's in dynamic equilibrium. All the forces are balanced, so the net force is zero. So this is essentially Newton's second law when you put them all together. So when we have a net external force, or an unbalanced force, it will cause an object with mass to change its velocity. This is the statement for Newton's second law. If anyone asks you what Newton's second law is, you say this statement. What is quite commonly said is that Newton's second law is F equals ma. Well, you know, it's not untrue, but it's not quite right. You're actually just telling me what is the quantitative relationship, which isn't really very accurate in terms of what is the law. So what this tells us is that 1 Newton will cause a mass of 1 kilogram to accelerate at 1 meter per second per second. It also tells us that unbalanced forces cause masses to accelerate or change their motion. So let's now take a look at a couple of examples here. Here we have a mass, a body, and we're going to apply a force to it. In this case, this is a 30 kilogram body. So let's apply this now to Newton's second law. So we have a net force equal to 100 newtons. And we know that the net force equals the mass times the acceleration. So if we substitute these values in, we're going to get 100 equals 30 times A. Now to make A the subject of this equation, I'm going to divide both sides by 30 and I'll end up getting an acceleration of 3.3 meters per second per second. And what do you know, off he goes. Let's look at another type of scenario that we can apply Newton's second law to. Here we have the same body and we've got two forces coming from both sides. Now, just like we did in kinematics, we're going to need to assign a positive or a negative to a direction. So, as always, going to the right we say is positive and to the left we say negative. So the net force in this scenario, as we've done previously, 80 plus minus 60, net force is equal to 20. So now all I'm going to do is substitute this into my equation again and I get 20 equals 30 times A. So I'm going to get A equals 0.6 meters per second to the minus 2. Now, I've got a positive value, so that tells me it's going to accelerate to the right. And what do you know, off he goes. Let's look at him again, our favourite little body here, and we're going to put it in a vise so that we have balanced forces on both sides. 1,000 newtons coming from the right, 1,000 newtons coming from the left. In this case, the net force is zero. So as long as that body can withstand that force, it's not going anywhere. In this case, it couldn't withstand that force. So now we've just taken in a whole lot, so we're just going to take a quick little brain break.
You have my sword. And you have my bow.
And my axe.
Okay, let's get straight back into it with a couple of scenarios, type questions that we can apply Newton's second law to. So, firstly, what force is required to accelerate a 120 kilogram barrel of Szechuan teriyaki dipping sauce 1.4 meters per second per second? This is really straightforward, and we're just going to apply it straight in, plugging in those values into Newton's second law. So we have 120 times 1.4, force is 168 newtons. Nice and easy. Let's step it up a little bit. 75 kilogram Scary Terry is chasing a victim at 8 meters per second. In 2 seconds, he changes his velocity to 5.5 meters per second. Calculate the magnitude of the force required to change his velocity. So, we can use Newton's second law, obviously, we're going to need to, but the problem we have here is we don't know what his acceleration is, so we have to go back to our old kinematics style equations and get a value for acceleration. So v minus u over t, change in velocity over time, will give us acceleration. So 5.5 minus 8 over 2 equals minus 1.25 meters per second. Now I can substitute those into Newton's second law, and I'll find myself with a nice equation equaling minus 93.75. So it has a magnitude of that, and the negative, all the negative does is it indicates to me that the force is applied in the opposite direction of motion. All right, final question. Ordinary 400 gram plumbus has 2 opposing forces applied to it, causing it to accelerate at 0.5 meters per second. The smaller force was 4 newtons. Calculate the magnitude of the larger force. Okay, so here's our plumbus. It's accelerating at 0.5 meters per second. Has a net force which is going in the direction of the acceleration. Now, here's where it's tricky. We have a smaller force of 4 newtons, and it has an opposing force, as it says that in the start, has an opposing force which must be larger because the net force is positive. The net force is positive, which gives us a positive acceleration. So I'm going to say that the net force, which is larger, the unknown force is larger, and it is going in the positive direction, and the smaller force is going in the negative direction. So now my net force equation, F1 plus F2 equals ma, will look like this. Negative 4 plus F2 equals 0.4. I've converted, and you see what I've done here, and something we need to be very careful of, is I've converted the grams into kilograms, which is something we must always do. The standard unit for mass is kilograms. So I've converted that to kilograms, 0.4 times 0.5, which gives me a value of 0.2 plus 4, so I end up with a force of 4.2 newtons. So these are all very simple problems that you're going to get if you apply this idea of net force, and we've spent plenty of time with net force, so we understand how to do net force equals ma. If you just break it all down, find the variables, apply it to the equation, it should be really straightforward.